General Implementation Requirements for Instrument Protective Functions IPFs, translating SEAL objectives into practical, field-ready systems. Implementing an Instrument Protective Function IPF requires more than selecting certified components. It demands a disciplined engineering process that transforms safety requirements into a fully integrated, operationally viable system. The purpose of general implementation requirements is to ensure that the IPF, once designed, is installed, configured, and maintained in a way that guarantees it will deliver the required safety integrity level SIL throughout its life cycle. These requirements bridge the gap between design documentation and field reality. They ensure that assumptions made during SIL assessment and verification are upheld during commissioning, operations, and maintenance. Design integrity must be preserved during implementation. Functional allocation. The full IPF initiator logic solver final element must be clearly defined, with each element responsible for a specific safety role. Shared devices must be evaluated for failure dependencies and common cause vulnerabilities. Separation from the basic process control system, BPCS, IPFs must remain logically and, where applicable, physically independent from non-safety systems. If shared infrastructure is used, independence must be demonstrated through design safeguards and failure mode analysis. Fail-safe philosophy. The system must default to a safe state on loss of power, signal, or internal failure. Final elements, e.g. valves, should be configured to move to a fail-safe position, such as fail-close, fail-open, or fail-locked, based on process risk. Installation standards for IPF components, initiators, sensors, transmitters, installed to minimize impulse lag, temperature drift, and vibration effects. Redundant sensors must have fully independent signal paths. Environmental protection, e.g. IP rating, shielding, must align with service conditions. Logic solvers, SIS-PLC, hardwired relays, mounted in appropriately rated enclosures with reliable power supply, preferably with UPS backup for critical functions. Inputs and outputs must be fully tested against configuration settings and functional diagrams. Final elements, valves, actuators, installed with verified stroke paths, accessible test points, and clear mechanical travel stops, must include feedback indicators and allow for partial or full stroke testing as defined by maintenance strategy. Verification and testing prior to commissioning. Function testing. Each IPF must be tested end-to-end, from simulated input to verified output action, under both normal and fail-safe conditions. Trip set points, logic thresholds, and output timings must match the Safety Requirement Specification SRS. Loop integrity checks. All signal wiring, termination quality, and ground isolation must be confirmed. Crosstalk, electromagnetic interference, EMI, and cable routing must be reviewed to prevent fault propagation. Configuration control and security. Access restriction. Modifications to IPF logic, set points, or device configurations must be protected by access control and audit logging. Only authorized personnel should be permitted to make changes, and all changes must follow formal management of change procedures. Tagging and identification. All IPF devices must be distinctly tagged, with SEAL critical devices visually distinguishable from standard instruments. Cabinets, junction boxes, and control panels associated with IPFs must be clearly marked and physically secured. Documentation, alignment, and verification records. Installed components must match the documentation, loop diagrams, SRS, logic narratives. Any discrepancies found during implementation must be resolved and recorded prior to final handover. Test reports, configuration screenshots, and calibration records must be compiled and retained to support future audits or investigations. Conclusion: implementation as the foundation of functional safety. No matter how rigorous the design, an IPF is only as good as its implementation. Adhering to general implementation requirements ensures that safety systems are not compromised by field deviations, shortcuts, or configuration errors. By enforcing disciplined installation, testing, and documentation practices, organizations convert safety intent into operational reality, delivering the integrity required to protect lives, equipment, and the environment. Robustness in IPF design and implementation, ensuring reliability under all operating conditions. Robustness is a foundational requirement in the design and implementation of Instrument Protective Functions, IPFs. It refers to the IPF's ability to perform its intended function reliably and consistently, even when exposed to adverse process conditions, environmental stressors, or operational disruptions. A robust IPF does not merely meet performance criteria under ideal circumstances, it continues to function predictably during abnormal, degraded, or high-demand scenarios. The goal is to create protection systems that are not only compliant on paper, but also durable and dependable in real-world applications. Robustness underpins trust in the safety system, especially when it is called upon during critical high-risk events. Designing for environmental and process stress. IPF components must be capable of withstanding the full range of ambient and process conditions they are exposed to, including temperature extremes. Devices must be rated and validated for site-specific temperature ranges, including cold startup conditions and heat exposure near process equipment, vibration and mechanical stress. Sensors and final elements must be mounted with adequate mechanical support to prevent loosening, signal drift, or fatigue failures over time. Ingress protection and corrosion resistance. Field enclosures, glands, and cable entries must meet at least IP65 standards, with materials selected for chemical and humidity resistance in outdoor or corrosive environments. Electromagnetic compatibility, EMC. Shielding, grounding, and proper cable segregation must be used to prevent signal disruption from nearby electrical equipment or lightning-induced surges. Operational robustness against human and system errors. A robust IPF is also resilient to operational variances, including power supply fluctuations. Devices must tolerate brownouts, voltage spikes, or brief outages. High-priority IPFs should be backed by UPS systems and surge protection. Process upsets and mode transitions. The IPF must respond reliably during startup, shutdown, or emergency transitions where process conditions may vary significantly from steady state. Operator interaction and misuse. Configuration menus, bypass switches, and manual overrides must be designed to prevent inadvertent disabling or misadjustment of the IPF. Physical and software-based interlocks should guide correct use and discourage unsafe workarounds. Diagnostics, fault tolerance, and degraded mode handling. Robust IPFs must detect their own impairments and provide clear, actionable diagnostics. Self-diagnostics and heartbeats. Smart instruments and safety systems should continuously monitor internal status and flag degraded performance or failure conditions. Redundancy and voting logic. Where single-channel reliability is insufficient, redundant architectures, e.g. two OBU3 sensors, dual logic solvers, improve fault tolerance and robustness. Degraded mode strategies. When an IPF element fails, the system must revert to a known safe state or activate compensating protection. Operators must be alerted through clear alarms, and predefined corrective actions must be in place. Robustness through lifecycle maintenance. Designing for robustness is only effective if maintained through operational life, proof testing, and partial stroke testing. Scheduled tests must confirm that devices still respond correctly to simulated demand conditions. Change control discipline. Robustness depends on configuration integrity. Uncontrolled changes to hardware, logic, or calibration can undermine system dependability. Spare parts and repair strategy. Fast replacement of failed components is essential for sustaining protection. Stocking, compatibility, and support strategies must reflect the criticality of the IPF. Conclusion. Robustness is a measure of real-world readiness. A robust IPF is one that delivers not just theoretical protection, but practical reliability under pressure. It is immune to nuisance conditions, designed to detect and manage failure, and resilient in the face of environmental, mechanical, and operational stress. By prioritizing robustness in every aspect of design, installation, and maintenance, organizations ensure that their protective functions are ready to perform when it matters most. Implementation of process-related instrument protective functions, IPFs, bridging process knowledge and safety integrity. Process-related instrument protective functions, IPFs, are designed to intervene in critical process deviations, such as overpressure, high temperature, low level, or runaway reactions that could lead to safety, environmental, or operational consequences. Their successful implementation requires more than selecting SIL-rated components. It involves integrating process behavior, instrumentation strategy, and protection logic into a single coherent system. These IPFs often serve as the final safeguard between a process abnormality and a major incident. Therefore, their implementation must reflect both detailed process understanding and rigorous functional safety discipline, aligning IPF design with process characteristics. Every process-related IPF must be tailored to the dynamics and constraints of the specific unit it protects. Key considerations include process safety time, PST, defines how quickly the IPF must act after detecting a deviation. All components, sensor, logic solver, and final element must operate well within this time frame. Trip set point accuracy and stability. Set points must be positioned to reliably detect unsafe conditions while avoiding nuisance trips during normal process fluctuations. Drift, hysteresis, and range limitations must be considered during instrument selection and calibration. Startup and shutdown conditions. The IPF must be designed to recognize and accommodate process conditions during transitional phases, avoiding false trips or masked failures. Process modes and alternate states. Some units operate in multiple configurations, e.g., bypassed flows, multiple feeds. The IPF must remain effective under all credible modes, or appropriate mode-sensitive logic must be implemented. Sensor implementation for process hazards. Redundancy for critical measurements. For high SIL applications, sensors should be installed in redundant configurations, e.g. 203 voting, to mitigate spurious trips and increase fault tolerance. 5. Sensor placement and response time. Sensor location must ensure timely detection of deviations. Long impulse lines, thermal lag, or poor mixing zones must be avoided. Validation of operating range. Selected instruments must reliably operate across the full credible range of process variables beyond steady-state design values. Logic solver implementation for process functions. Cause and effect integration. Logic solvers must reflect defined process responses to deviations, including time delays, interlocks, reset conditions, and permissive logic. Manual reset and alarm integration. Where applicable, the IPF should incorporate manual reset mechanisms post-trip to prevent automatic restarts. Alarms linked to IPF activation must be clear, prioritized, and traceable. Bypass logic for maintenance. Bypass capability should be limited, controlled, and accompanied by alerts and compensating measures. All bypass operations must be logged and reviewed as part of functional integrity assurance. Final element implementation for process control. Valve response and stroke time. Final elements must actuate fully and reliably within the defined process safety time. Partial stroke testing or live monitoring should be considered to detect degradation or sticking. Fail-safe design philosophy. Actuators and valves must move to a defined safe position upon signal loss, power failure, or internal fault, aligned with the specific process risk. Energy source reliability. Pneumatic, hydraulic, or electric power supplies must be designed to maintain function during abnormal scenarios, including pressure loss or blackouts. Commissioning and performance validation. End-to-end function testing. Each IPF must be validated in full, from process condition simulation to trip actuation, to confirm functionality under realistic operating scenarios. Set point verification and calibration. All trip set points must be verified against process safety analysis, and calibration tolerances must support reliable triggering. Integration with safety and operations teams. Operators and maintenance personnel must be trained on how the IPF behaves, how to respond to trips, and what constitutes an abnormal condition. Conclusion: process-related IPFs demand custom, risk-based implementation. Implementing IPFs for process deviations is not a generic exercise. It requires direct alignment with the process dynamics, safety targets, and operational modes. By addressing detection, response, and reset strategies through a process-informed lens, these functions become reliable, effective barriers that protect plant integrity. Their success lies in thoughtful integration, where engineering discipline meets deep process insight to deliver SIL-compliant real-world protection. Instrumented Protective System, IPS. Coordinated safety through layered instrumentation. An instrumented protective system, IPS, is a coordinated arrangement of instrument protective functions, IPFs, that work together to prevent hazardous process conditions from escalating into incidents. While an individual IPF addresses a specific risk, an IPS is a broader system-level construct that integrates multiple IPFs, across initiators, logic solvers, and final elements to form a complete layered protective strategy. The IPS is typically independent of the basic process control system PCS and is designed to act as an automated fail-safe safety layer. Its role is to detect deviations, execute predefined logic, and initiate protective actions, such as equipment shutdown, isolation, depressurization, or emergency venting, before process parameters exceed critical thresholds. Characteristics of a well-designed IPS. Functionally and physically independent. The IPS must be isolated from normal control functions to ensure that failures or changes in the BPCS do not compromise safety. Independence applies to power supply, signal paths, I/O modules, and configuration access. Composed of multiple IPFs. Each IPF within the IPS addresses a distinct hazardous scenario. Together, they provide holistic coverage for high-risk process conditions. Built to meet specific SIL targets. Every IPF within the IPS must meet its assigned SIL, and the overall system architecture must support the highest required SIL across its functions. Predefined and predictable response logic. The IPS must execute logic based on cause and effect matrices with deterministic outcomes that are auditable and testable. Fail-safe by design. The IPS must move the process to a known safe state upon detection of failure conditions, loss of input signals, or logic solver malfunction. Components of an instrumented protective system. Initiators, sensors or detection devices. Monitor key process variables and deviations, e.g., pressure, level, temperature, gas detection. May include redundancy or voting schemes to improve reliability and reduce nuisance trips. Logic solver safety controller receives input signals, evaluates logic, and initiates protective action. Must be safety rated, e.g., SIL certified PLC or hardwired relay logic, and support diagnostics, event logging, and override management. Final elements, actuators, valves, breakers, execute the physical response required to neutralize the hazard, must respond within process safety time, and include fail-safe mechanisms. Integration and coordination with plant systems. Although the IPS is independent, it must be effectively integrated with the broader plant infrastructure. Alarm systems. IPS activations should trigger clear, high-priority alarms for operator awareness and response. Alarm rationalization must avoid overload and ensure correct prioritization of IPS-related events. Emergency shutdown, ESD hierarchies. The IPS often forms part of the overall ESD system, supporting multi-tiered shutdown sequences and interlocking with utility or auxiliary systems. Fire and gas systems, FGS. IPS may receive inputs from or share logic with FGS elements, especially in integrated protection strategies. Human-machine interface, HMI visibility. Operators must have visibility into IPS status, active trips, bypass conditions, and test results, without the ability to inadvertently disable protection. Maintenance and reliability assurance. Proof testing. Regular proof testing of each IPF within the IPS is required to validate integrity and maintain SIL compliance. Where full tests are impractical, partial stroke testing or simulated input methods must be used. Bypass management. Bypasses must be authorized, logged, and accompanied by risk mitigation measures, e.g., temporary monitoring, procedural restrictions. Event logging and review. IPS responses, faults, and manual interactions must be logged and reviewed for compliance, performance tracking, and continuous improvement. Conclusion: IPS as the backbone of functional safety. The instrumented protective system transforms individual protective actions into a coordinated, systematic safety barrier. When implemented with rigor, it offers high reliability, fast response, and audit-ready performance that safeguards people, assets, and the environment. A robust IPS ensures that when process conditions exceed control limits, protection does not depend on chance. It depends on engineered certainty.